Hello, Drew. Okay, so since we are at the start time of the class, welcome back to my course in a new session, and hopefully we're gonna get joined by the other students soon. This is an introductory circuit analysis course, which is essentially going to be the DC circuit analysis, and part of it, you may have had some experience in a physics course where you have done some possibly a circuit analysis techniques. So it'll be sort of expansion on those ideas, and we will be basically getting in more detail, in-depth techniques of DC circuit analysis. And so let me share with you the syllabus, and then I'll kind of talk about briefly the assessment techniques and also some useful resources that are available in our announcements. Okay, so this is the syllabus addendum. It's a general syllabus which has some sort of standard information that is very common to all the courses as far as the academic integrity policy, other school policies, late policies, etc. So all that is going to be listed in that main syllabus. But this is syllabus addendum. You can find my biography there. Just give you some familiarity with my background. Also, here some key assessment criteria. As you could see, there are going to be live chats like this on a weekly basis. So we'll have 2 weekly live sessions. Typically, I try to keep it around 75 minutes, but then depending on how the requirement of the material that need to be covered could be increased. And if we keep it at 75 minutes, then the balance of the time, since we have 2 hours dedicated to this session, could be used for office hours, where you can discuss any questions about the assignments or anything that we talked about over up to that point in time. So live chats are very good place to interact with your fellow students and myself. The discussion boards is another assessment criteria for us, where some of the topics will be discussed ahead of time, and the idea behind that is so that you can do a little bit research ahead of time, and sort of when we get to that material, you will have some flavor of that. In that sense, it's going to be a little bit easier to sort of follow the lecture and also work on the assignment. So the discussion boards also are an important component of your course. Then there are individual projects which are broken down into homeworks and lab assignments. So there will be some simulation lab assignments, just like we did in the previous course, the digital one. The multisim is a very good tool to perform simulation of your circuit, and that way you can see the waveforms and the output, and various DC components could be placed there, and that way you can simulate your circuit and kind of see where we are there. And finally, the other assessment criteria is the exam. So about 50% of our assessment will be done through the exams. Then 300 or 30% is through individual project, which is homework assignments and the lab assignments. And then there'll be a weekly discussion forum, as I mentioned. So each week, 20 points are dedicated to each discussion forum. So we have a total of 10 discussion threads, and basically 20% of your overall grade depends on class discussion. So if you participate actively in these discussion threads, that gives you about 20% of the total grade, and just requires a little bit of research on the topic, and maybe just shares your ideas there. And so that's kind of an important piece of this overall assessment. Finally, the textbook. So this is the textbook. You should have access to it, so you can download it and view it offline. The Analysis and Design of Linear Circuits, 3rd edition, by Thomas. So that is the textbook that we're going to be using. As far as the course description and the learning outcomes, I mean, these are taken directly from the catalog, so you can, view these. These are the techniques that are going to be covered in this course, and some learning objectives, as well as the course description, as you could see up here. The tentative schedule for this class is listed here. So we will be covering about 4 to 5 chapters, depending on time. I mean, I've listed 4 chapters here, but if we have time, we'll cover a little bit more. And they are sort of broken down as far as the weekly tasks are concerned. And then you could also see the various tasks that are going to be due throughout the term. And these are in addition to discussion boards, every week you could see that there's one assignment almost on a weekly basis. It could be a homework, it could be a lab, it could be an exam. So that sort of gives you the, what to expect in this term. Okay. Now, let's come to the main page of the course. I want to show you a few useful announcements that are listed here, which should be helpful in completing the different assignments. I mean, you can see the rubrics that are listed there. You can see there's a late policy that is listed there, which should be a guideline in case you miss any assignments. So that should be referenced there. Then the discussion board rubrics are listed here. Homework assignments, rubrics. And also rubrics for the lab assignments, the format in which the lab should be presented. This is very detailed information there, and how the lab assignments are going to be assessed. So all that information is present here. And finally, the rubrics for the exams, which are very similar to the rubrics for your homework assignments, because of course it's going to be problem based, both of these assignments. So therefore you need to review them. In addition to that, there's be weekly announcement which are going to be focused on the topics that we're going to be covering through that week, and also some other useful resources may be shared through the announcements. So it's good to pay attention to these announcements, and I mean they have some helpful information for you there. Okay, so as I mentioned, this is the introductory circuit analysis course with the prerequisite of physics. So hopefully you have had that course taken already, and that should give you some background in circuit analysis. So the first chapter of the textbook is mainly the introduction So in this chapter, various topics are introduced in the sense that, the units and the type of various important concepts in terms of voltages, currents, sources, some nomenclature that is very useful in this course is discussed there. So it's basically just setting up the discussion for you. And then basically we build upon that. The real circuit analysis techniques that are going to be covered are going to be starting chapter 2. So chapter 2 onwards, and each chapter has quite significant involvement in terms of the ideas that we'll be discussing. So we talked about the various criteria. So let's do a basic definition of what electrical engineering is. Okay. Since this is an introductory course, so a lot of the information I'll present would be very sort of foundational. Okay, so a definition of electrical engineering that can be described is the study of processing energy and information. Okay, so that's and that really should sort of tell you, the two distinct paths of electrical engineering. So when we talk about energy, these are the areas which are traditionally been known as electrical engineering focus areas, which could be, power generation and distribution. So circuit analysis is a very big component of this area. Then another area is electromagnetics. So, I mean, a lot of electrical machines follow these principles. I mean, just large scale um, um, electrical machines that are basically the industrial revolution in the last couple of centuries has been, due to the innovations in electrical engineering principles. So those are the electromagnetics is at fundamentally a very important concept there. And also, one of the areas which could be sort of listed in both these is electronics. I mean, fundamentally, I mean, they have to do with physics, so therefore I've listed it as in terms of energy, but of course it is used for information processing. So that's one area. The other area, of course, is computers. So, your ones and zeros, as you have seen in the previous digital analysis course, digital logic design course, where, we are processing information. And that has been in the last, I would say, 40 to 50 years, has been the source of significant innovation, where, a lot of new devices came up. Computers were revolutionized in terms of the personal computer, and then of course later on mobile devices, internet, all that has changed the way we live our lives these days. So other areas that are information processing, of course, are communication. So that'll be your cell phone data. Similarly, control systems. So a lot of industrial applications are certainly using the control system, and a lot of automation is very important to our industry. And control system is at the forefront of that area also. And finally, signal processing. That is also one of the areas that can be classified as signal processing. This is sort of a broad definition of electrical engineering. And if we have to sort of screen has frozen for me. Let me just see. I think I should start using OneNote. I think it's probably a better, more stable tool. Oh, okay, all right, it's back. Just give me a moment. All right. I apologize for that. So Let me write this statement and I'll explain it to you in a minute. Okay, so those are the two main principles which really are important for circuit analysis. So the separation of charge, which is a technique, essentially it's a way of describing voltage in our circuit. So that creates the separation of charge, creates electrostatic force, which is the driving force in our circuits. And then the charge in movement, that is when the flow of charge, essentially that is the current. So the two important concepts of circuit analysis are current and voltage, right? So when we talk about current or charge and movement, so the charge is bipolar. Meaning that if I were to write the charge on an electron, it is going to be minus 1.602 into 10 raised to the power minus 19 coulombs. Okay, so that's the charge on an electron. It's a negative charge. But if we were to, there is an equal charge on a proton, but it's opposite in polarity. So that is plus 1.602 into 10 raised to the power minus 19 coulombs. So this is my charge on an electron. And this is the charge on a proton. Okay. Now, when we talk about current, the flow of this charge is essentially how current is described. So we can say okay. So in other words, and the units are coulombs and seconds. So the current can be quantified in terms of units is coulombs per second. Okay, and there's a simpler unit that was described later on, and that is called amperes. Okay, so that's how we come up with the unit for current. Okay, so it is classified as coulombs per second or charge per unit time in terms of the flow. And as I mentioned, the charge is bipolar. So if you had, you can have a current that is described as such. So for example, if I have 1 ampere current that is shown from left to right like that, typically, I mean, when you see a circuit with the arrows, the current is displayed, that shows the direction. So that is exactly the same if I were to describe it like this. Okay, So, I mean, there is a passive sign convention, which we'll discuss in more detail, but if everything is written correctly, regardless of what assumption you take in terms of direction of the current, if the circuit is balanced, then essentially the signs take care of itself, and the passive sign convention would dictate that your circuit is balanced. So therefore, if I were to show a current flowing from left to right, in positive sense, the right to left one is going to be negative, which essentially is the same thing. Okay. And one of the important thing here is to say that it is a vector quantity. So current is a vector quantity meaning there is a direction and magnitude. Okay, so that's kind of important to understand one thing about current. Okay, so that then let's move on to the voltage now. So due to the separation of charge, the work that is done per unit charge is called voltage. Okay, so let me describe it as and it can be described as like that. Okay, so any work done per unit charge is what the voltage is, and the units for work are joules. So joules per coulomb is going to be the unit for voltage, or for simple, it is indicated as volts. Okay. Again, this is also a vector quantity. So, I mean, typically, initially, when we discuss these circuit components, we use these boxes, but later on, of course, we will have resistors and voltage sources and current sources, etc. So for now, we'll just use this, the box convention. So for example, you can say this is 5 volts, and the equivalence, as I mentioned, this is also a vector quantity. So it has the magnitude as well as direction. So if I were to write it in opposite sign, then we can say minus 5 volts. Okay, they are the same. It's just that the polarity could be, represented differently. Okay, now another important concept is the power and energy. So let's talk about that. I mean, this is a lot of very general information. I'm sure you have seen it in other courses, but I want to, get this out of the way before we get into the real nits and grits of this course. But this first couple of sessions are going to be like that. After that, we're going to get into the more important techniques of circuit analysis. So power and energy, so it may be seem redundant information at some point, but again, it's important to cover. So power is the rate of energy transfer. Okay, that's the definition of power. Okay, so P is equal to so that's the work per unit time. And in other words, we can write it like this: per unit charge the same thing if we describe it like that. So if you look at this, the first component, that is voltage. And the second component is current. So the power could be described as such. The units for power are from this definition is joules per second. Okay. In other words, a simpler unit, since we have simpler units for all of these, is a watt, okay, as you know. Let's briefly talk about passive sign convention. We'll talk about it in more detail next session. So we have in our circuit, we have passive elements, which are load, and a load typically what it does is it absorbs energy, right? So a typical example of a load is going to be a resistor. So whenever we use resistors in our circuit, they absorb energy, and you could see it as in terms of a heat. So whenever you have a circuit running for a while, if you touch a resistor, it typically would be a little bit warmer, and that is just a sign of that it is absorbing energy. Okay, so the passive elements are loads in our circuits, and what they do is they absorb energy. And again, using the same convention for now, we use these boxes. So current is shown, and okay. So for passive element, as part of the passive sign convention, the current will be entering through the positive terminal. Okay, so that's kind of an important distinction. And when it is entering to the positive terminal, that means that the power dissipated by that device is going to be positive, right? So in other words, it is absorbing power, right? So we can say that as part of this passive sign convention, the load or passive elements absorbs power, and in other words, the direction of current is positive to negative. Okay, so that's very important there. Okay. Okay, so the next type of device is active elements within the circuits. Okay, so in other words, for active elements as part of the passive sign convention, you will see that the direction of the current is going to be um, essentially minus to plus. So the current is going to be leaving the positive terminal of where the voltage is represented. So in other words, if I show my voltage like that, the current is going to be in this direction, meaning it is leaving the positive terminal of that that active element. So when we describe the power, again, it's going to be minus VI. Again, the way we count the voltage is in the direction in which we're counting it is where the negative sign comes from. So we're sort of going from bottom to top here. So therefore we consider the negative sign there. Okay, so that's why you have a minus VI. Okay, so power dissipated by an active element is always a negative value when we talk about passive sign convention. And what that means that if it is absorbing negative power, that means that it is producing power and actually supplying that into the circuit. Okay, so let's write that statement here. So a voltage source would be a typical example of active element. You can also have a current source, So a voltage source is like typically your batteries. I mean, so any 12-volt battery or 1.5-volt battery, that is your voltage source. An example of a current source is like a photovoltaic cell, which when activated through solar energy, can produce current, and that current can then be supplied to the rest of the circuit. Okay. Okay, so that's basic description and definition of active element. Okay, so let's look at something else here. Let's look at an example of a generic circuit. Again, for today, we'll be using this box convention. Later on, I will use the actual components. Okay, so let's describe some terminology here. Okay. Node is a point where two or more elements can be combined, or they join together, right? So we can describe a node as a point in circuit where two or more elements So if you look at this this particular circuit example, so we have a node here. Okay. Then we have another node here. Essentially, this is the same node, because there's a wire in between, and wires we do not consider as circuit elements. Okay. And then the same thing for the bottom. I mean, these three are together. So we can say this is node 1. This is node 2. And this is node 3. So there are a total of 3 nodes in this circuit. Okay. Let's consider loops. Okay. Let's define the loop first, and then we'll see how many loops we have in the circuit. So any closed path in a circuit is called a loop. Okay, any closed path. Okay, so okay, so in this case, if we look at this, so we have this loop here, another loop here, and then of course there's the outer version, outer loop as well that combines the two. So that could also be considered as loop 3. Okay, so we have a total of 3 loops in the circuit. Okay, now there's another important term here, which is called a mesh, and we want to distinguish the mesh from the loop. Is that a mesh is also a loop, but it is a loop that could not be subdivided, right? So in this case, then basically the loop 3 is not a mesh in this case, but loop 1 and loop 2 are meshes. And the reason we do that is, as we move forward, this is a very important circuit analysis technique called mesh analysis. And that there's a technique where we determine the analysis of circuits. And so therefore meshes become very important. So the mesh is a loop not containing any other loop. So it's just sort of the basic unit of a loop. Okay. Okay. So if we were to describe it, so a mesh is a loop that could not be broken down into any smaller loops. So in this case, L1 and L2 are our two loops. Sorry, two meshes. Okay. So based on these nodes and meshes, there are two techniques for circuit analysis, and those techniques are described in Kirchhoff's laws, and we will briefly talk about it here. The first law of Kirchhoff is called Kirchhoff's current law. In other words, it's called, in short, KCL. Okay, KCL is the short in which we know it. Okay, so this is a conservation of charge law, which means that around any loop, the sum of all the currents must be equal to 0. Okay, so so in other words, the current entering the node is equal to the current leaving the node. Okay, and we can describe it as such. Okay, so at the node, the sum of all the currents is equal to 0. And as I mentioned, this is the conservation of charge law. And of course, we'll be discussing it in much more detail later on in this course. The second law that Kirchhoff described was so it's Kirchhoff's voltage law, or KVL for short, and it's a conservation of energy law. Because the source of energy in a circuit is the voltage source. So therefore, since we're looking at voltages there, we can then say that so sum of voltages around a mesh in a circuit is equal to 0. Okay. So over here, we can say that the sum of all voltages around a loop so essentially, I mean, these two laws are sort of a litmus test for you, right? So if you see that, and if a circuit is not obeying these two laws, then essentially it's not a valid circuit, and there's something illegal about it. So that's sort of, a criteria by which you can evaluate the circuits. Okay, so let's move forward and talk about the sources. Again, we're talking about the elements, the circuit elements, just to set up our discussion for more detailed circuit analysis. So ideal sources. Okay, so a voltage source or a DC voltage source is represented in a circuit like that. Okay, by a V. And of course, it is an active component. So therefore, the current entering is through the negative terminal, right? So this is the source of energy in our circuit. So therefore, this is the passive sign convention by which we represent our ideal source. Okay. And the description is this. Okay, so it does not describe the current basically the current will come into picture when we bring in the load. So typically your IV characteristics for the voltage source is described as such. So your V and I. So depending on where the voltage level is, you will have some voltage shown here. Okay. So for example, this could be, V sub I, for example. Okay. That's the quantity. Okay. Again, example would be, a 12-volt battery is a typical example. Now for ideal current source, the symbol is described as such with an arrow. Okay, and as I mentioned, an example of that would be a solar photovoltaic cell, which is a source of current, and description is this is just like we did for the voltage source. It's independent of the current. Over here, it is independent of the voltage, and just like we did the IV characteristics for the voltage source, the current source, you will have some, for example, I sub S like that. Okay. So when the loads come into the picture, then of course we have the current in the voltage source and the voltage in the current source. So that discussion, the power dissipation will come into picture at that point. Okay. So these are the ideal sources. There is also another type of source that you will see in your circuit, and those are the dependent sources. And the dependent sources are typically used for modeling of circuits, and we see it a lot in electronics. We also see it in circuit analysis, and especially when we get to the op amps part of the discussion in this course, you will see a lot of these dependent sources. So dependent source is the quantity of that source is actually described by some other part of the circuit. It could be a resistor, it could be a voltage source, it could be a particular voltage or current in a particular part of the circuit. So let's do a description there. And there are actually 4 types of them. So I'll describe all 4 of them for you. So they are called dependent or controlled sources. So let me just write the description and we'll talk about it. The voltage or current okay, and it is represented by this diamond shape. Okay, so that's how they are represented. And the four types. So this is a voltage controlled source. Okay. So basically there'll be some quantity within the circuit. So it will be another voltage source multiplied by some constant value is how that value is described. Okay. So that's one of the types. The another type is okay. So that's a current control. Again, you have a constant and the value of the current source, or it could be a current in another element as well. The third type is again the current source now. It's a dependent current source, which could be something like this. Again, it's a voltage in another part of the circuit times some constant. And finally, the current source could be some so we'll see all these different types as part of our analysis as we go forward in the course. Now, to focus our discussion more on what we'll be using it for this type of elements. So one of the other important element of your circuit is going to be your resistors. Okay, so typically when we do circuit analysis, there are, of course, we'll discuss capacitors and inductors also later on, but initial discussion is going to be about a resistor. So there'll be a resistor, there will be a voltage source, there'll be a current source, currents, voltages, etc. So that's going to be pretty much for more than half of the term. We will be evaluating our circuits based on the resistor, voltage, and currents. Okay, so a resistor is our typical load in a circuit. So again, it's a load, so it's a passive circuit element, and it absorbs energy. Okay. And the Ohm's law description is such: V is equal to IR. I mean, I'm sure you have seen this. So the voltage in a resistor is dependent on the resistance and also the current that is flowing through it. Okay, so the resistance, which is the unit, is V over I. I mean, of course, we manipulate this. And this is volts per amp, as we have derived our units earlier. In other words, ohms. Omega is the sign typically we use for it, or OMS, ohms, is also used. Okay. When you talk about the power in a resistor, so the power is VI. So then you can, V could be described as IR times I. So power of a resistor could be described as I square R. It's one of the formulas. Similarly, this could be manipulated as VI or I square R or V square over R. Okay. So those are the different forms, depending on what is given to you in the circuit. You can perform the calculation of power based on these different formulas. Okay. And finally, conductance is another quantity. It is represented by G, and that's basically a capacity of conducting current through a circuit. So that is what conductivity refers to. So G is essentially the reciprocal of resistance. So G is equal to 1 over R, and in terms of units, of course, it becomes opposite, so it becomes amps over volt. And in other words, Siemens is one of the units that is used, but one of the other unit that is very commonly used is just a reverse spelling ohms, so MHO, it's like ohm in reverse. And also the symbol for that is an upside down omega. So that's the symbol of conductance, or the unit is Mohs, Siemens, either one are fine. Okay, so I think this should set up our discussion quite well going forward. So today I'm just going to stop it here. And basically, the first chapter is a very general type of information, and it's wanted to go over certain of these ideas, and these quantities are very important when we're doing the circuit analysis. So it's important that you know all of this, where these units come from, and how they can be used. So what we'll do is, in our next class session on Thursday, we'll proceed with this discussion further. Are there any questions at this point?
Nope.
Okay, great. All right, so if there aren't any questions, I'm gonna stop the session, and I thank you for your time here attending the session. I really appreciate it.
Thank you.